So hello everyone. My name is Marc Dubois. You might not know me, at least from the MetaMAT's, but I'm a good friend of Sebastian and Bogdan, who and Muammer, who are running this seminar. And I thank you for inviting me to share today's session, which is going to be a talk given by Chengzhi Shi from, as you can see, the Georgia Institute of Technology. In like a few words, had the pleasure to meet and to work Chengzhi when I was postdoc in Berkeley. Chengzhi was a PhD student. We worked together, I think, for 2014 to 2016, and he kept finishing his PhD, so in Professor Zhang lab in Berkeley. And he joined after the Georgia Institute of Technology, and so in the mechanical engineering department, and also some acoustic application for bioengineering and bioscience. I've seen following him on social network, like he won quite lately some prestigious award from the National Science Foundation and the Office of Naval Research, and I'll be glad to see what's the new stuff he's been working on. So Chengzhi, feel free to start.
Yes, thanks Mark for the very nice introduction, and very nice to see you again. And good morning, good afternoon, good evening, depends on which time zone you are in now. So I'm Chengzhi Shi, Assistant Professor of Mechanical Engineering at Georgia Tech. So today what I'm going to do is I'm going to share with you my exciting research on metamaterials for medical ultrasound. So at Berkeley, Mark already mentioned we work together on the metamaterials for acoustics. And now I move on to actually study more by increasing the frequency, and then move on to the medical ultrasound to see how metamaterials can be used to actually help people with the treatment and imaging. So first of all, just in case, I don't know why. Okay, now it goes. Okay, just in case you don't know what's acoustics, Wikipedia actually gives us a very nice definition, even though a lot of people say that you don't trust Wikipedia, but at least this definition is correct. Okay, so the branch of, well, acoustics is actually a branch of the physics that deal with the study of all mechanical waves in gas, liquid, and solid. Okay, and this includes the propagation of the vibration of sound, the ultrasound, and infrasound. So with this definition, I would like to do some kind of interactiveness in this talk here. So when I talk about this definition of acoustics, what is the first thing you could think about? Feel free to unmute yourself and then give me some kind of thought. Anyone? Just don't be shy. Yeah, Mark?
I will start. I will think about music.
You think about music. That's right. That's the sound we hear, right? I'm sorry for my voice. I may just catch flu since I just fly back from NIH last week. So we can think about this, the music. That's what we hear, the sound we hear. What else? When talking about acoustics. Anything else? So I'm not sure whether you are married or not. If you are and you have a kid, you'll probably go to the hospital and see this. Right? So that's the ultrasound. That's when the doctor actually used the ultrasound probe to try to actually visualize the baby in you or in your spouse. And that's usually the standard way of like doing this like OB examination nowadays, right? Because like it's cheap and it's convenient. So that's another thing. And there could be some other things. One thing is, look at this definition. We just talk about sound, we talk about ultrasound. So now we can have something called infrasound. So what is infrasound? Anything you can think about? Just don't be shy. I'm not sure if you are familiar with one thing or one phenomenon that's like happening around the world, especially along the coast where like there's fracture of the plate of the earth. But since Mark and I were from Berkeley, so we are very familiar with this thing called earthquake. So this was actually the damage of the earthquake in 1989 in the Bay Area, which crashes the Highway 80 in the Bay Area. And there was a lot of casualty because it was happening during a rush hour when people just drive back home in the evening. So there was a terrible story, but nowadays we are studying this earthquake, which is the infrasound, which has a much lower frequency than what we can hear, but it's a type of infrasound. And a lot of people are trying to actually study how can they actually deal with the earthquake to reduce the damage to the infrastructure and also the buildings to save lives. And in terms of saving lives, we actually have some other applications of the acoustics that can save lives. So the next thing I'm going to talk about is something called the high intensity focused ultrasound, which people also refer as HIFU. So nowadays, people can actually use this focused ultrasound with high power at the focal spot to just ablate the tumors. And this is one example of the HIFU ablating the liver tumor in vivo without cutting through the patient. So with this technology, nowadays, without doing the surgery, you can see the patient go back to work the next day of the surgery, other than staying in the hospital for a week and recovering from the cut of the surgery. So with the advance of the technology, now we have this treatment method as well. And of course, if you move higher into the frequency, you can have this kind of something called ultrasound microscopy, which move much higher frequencies. And then you can use it to actually see much smaller structures like molecules because the wavelengths of the ultrasound is much higher. And then even though it's still diffraction limited, but because of the small wavelengths, you can see the small details of the structure. So I basically cover all the spectrum of the acoustics from infrasound like the earthquake all the way to the acoustic microscopy, which goes beyond gigahertz. Okay. And today, in the story I'm going to share, I will focus mostly on these two things, the imaging and the therapy, because that's the research I'm focusing on currently. So talking about the imaging, we just shared the story about using the ultrasound to view the babies inside the body. But the question is, have you ever heard about using ultrasound to look at the brain? Anyone? Don't be shy if you heard about this. Yeah, Mark?
I think I've heard it like in the lab. I knew people were able to do it on young kids because the skull is not closed.
Exactly. Usually it happens for the infants when the skull is not closed. But for adults, we could never do this kind of ultrasound imaging of the brain because of the skull. So what happens? Nowadays, for animal study, especially for these mice in the Nature Method paper, what they did was they opened the skull and then have an ultrasound window to view the brain inside. Okay, so what happens if you don't just like cut the skull and create this kind of ultrasound window? Sometimes people may claim that, well, I have some window on the side of the skull that's like a very thin skull, and then you can try to image through that. But the thing is that window is too small, that the aperture is very small, and which leads to a very bad resolution because of the aperture. So let's see what happens if you have a sick skull and you try to image through. When you have a sick skull, and let's just put an ultrasound transducer through the skull, and let's just assume this is submerged into water. Actually, in the real clinical setting, what happens is this is not water, but instead you will replace this with ultrasound gel, which has similar properties of the water here. So in our study, we just like use the water to be simplified, and then try to see if the ultrasound can get into the brain. Okay, so what happens? First, we know what's the skull parameters, which is given by the previous measurements. There are people who was doing testing of the acoustic properties of the cranial bone in the 80s using the ex vivo human skulls. So we use these parameters from their measurements, and then we just do the full wave simulation and then see what happens by sending an instant ultrasound into the skull. And the ultrasound we send is at 1.5 megahertz, and then see what happens. So normally we should expect some transmission and some reflection. So let's see what happens. When we plot the sound field along this transmission line, we will see this result. So the blue curve here represents the pressure field, and the red curve represents the amplitude of the pressure field. So you can see what happens here is you can see a lot of interference, which indicates the interference between the instant wave and the reflection wave. And the transmission is very low through the skull, which is kind of expected because of the impedance mismatch between the skull and the ultrasound gel and also the brain, right? So the question is, how do we deal with this impedance mismatch? There was some design called a complementary metamaterial. And what happens is they are trying to design a layer of complementary metamaterial that has the negative density and bulk modulus of the ablating layer. So what happens is if you assume this is the skull, and then you try to use the metamaterial to achieve the density and bulk modulus to be the negative value of the ablating layer, then they did the simulation and then see that without the ablating layer, you can see when they focus the ultrasound towards that ablating layer, what happens is you have a strong reflection. And of course, without the ablating layer, you focus it through, right? But with the complementary metamaterial, what happens is the complementary metamaterial matches the impedance with the ablating layer, and then it allows the ultrasound energy to transmit through the ablating layer. So that's what they presented in their story. But is this the end of the story? The answer is probably not. Otherwise, I wouldn't be even talking about this here, right? So let's see what happened if we put the ablating layer to be an actual skull here. So let's just try to use the complementary metamaterial as they designed. So the negative value of the density, and here I use sound speed. So sound speed density is interchangeable with the bulk modulus and density here for acoustics. So what happened is we use the actual parameter of the skull and then use their design, which is the negative density and negative sound speed for the complementary metamaterial, and then send the ultrasound at the same frequency and then see what happens to the transmission line, okay? So if we send the ultrasound at 1.5 megahertz and we measure through the transmission line, what happens is you'll still see the interference of the incidence wave and the reflection, and the transmission is still very low. Same thing if we flip the ultrasound incidence direction, what happens is you still see the beating or the interference between the incident wave and the reflection, while the transmission through the bilayer is still very low. And the reason we need to look at the bidirectional transmission line is because when we are doing imaging, the ultrasound imaging, especially the B mode imaging, is based on the scattering of the ultrasound, which means that we need to send the ultrasound through the skull into the brain. And also we need to collect the scattering signal, which is backscattered from the brain through the skull backward, right? So the question is, what actually happened here? Why the complementary metamaterial designed by the previous paper didn't actually do its job? The answer lies into this imaginary part of the density and the sound speed here. So what is the imaginary part in the effective medium of the density and sound speed here? Actually, this imaginary part actually corresponds to the energy loss of the acoustic wave. So if you are familiar with acoustics and also effective medium theory, we can always use a complex value to represent the effective median. And then the imaginary part will just tell us what's the loss of the skull. So why the skull has a loss is because the cranial bone is porous, and porous medium is lossy for acoustic wave. It's like the sound absorbing sponge that you put into your speakers to absorb the sound around it, right? So that's the same thing for the skull. So then the problem is we have the loss from the skull that was not considered by the previous design. And also remember that for acoustics, the acoustic impedance of the skull is actually given by the product of the density and the sound speed. So what happens is if you take the product of these two values here, the imaginary part will actually affect the real part of the impedance. So if you just consider the real part of the effective medium parameters, then you are not taking account into the contribution of the lossy part to the acoustic impedance. Okay, so the way to do is instead of just like ignoring the loss of the skull, what we do is let's just take that into account. Okay, so we choose to design our non-Hermitian complementary metamaterial using the parameter that's the direct opposite of the complex value of the density and the sound speed. Okay, and then let's see what happened in the transmission line. So if we use this non-Hermitian complementary metamaterial and then send the ultrasound at 1.5 megahertz through the bilayer, what happens is we can see that we had a total transmission here through the bilayer. What about the backward transmission? Same thing here. We have a total transmission through the bilayer, which means that now with this non-Hermitian complementary metamaterial, we can achieve a total transmission through the skull. So we achieve this transcranial ultrasound, which can be used later for the brain imaging. Okay, so let's just look at the full wave simulation, see how this will help for the ultrasound brain imaging through the skull. Especially, we are looking at how this will image a brain tumor. Okay, so let's just simplify the model just underwater and then send a plane wave through it. So we are using a plane wave imaging method to achieve our BMO imaging. And then what you can see is we are taking the field in this window, which is close to our ultrasound probe. That's what you would measure or what you will read from the RF signal of the ultrasound probe. Okay, and we take a line, which is the scattering signal you will read from your ultrasound machine. So here you can see the shadow of the scattering of the tumor, which helps us to actually reconstruct the tumor in the BMO imaging of the ultrasound. What happens if you have a skull? Let's still look at the same window and the same line of the ultrasound probe, and then see what happens. So what you see is just a lot of just a noise level being increased. So what you see here is actually just a reflection of the ultrasound from the skull, and you get no information about the brain tumor here. So there's no way you can actually reconstruct the image of the brain tumor through your BMO imaging. Okay, how about let's use the complementary metamaterial that was designed by previous group. What happens is let's just look at the same thing. You can start to actually see some slight variation that may give you some information, but that information is too low that the signal to noise ratio is very low, that it's hardly for you to actually reconstruct the image of the brain tumor through your BMO ultrasound. Okay, but how about we use our non-Hermitian complementary metamaterial? Then now you start to see the shadow again. And that's how you reconstruct this brain tumor inside the inside your BMO image. Okay, and some may actually argue that, well, your simulation here is actually treating this skull as a fluid like a medium, which is the effective medium theory, but actually the skull is extra solid. So your result may be like wrong, or something may happen when you actually use the solid model to model this skull. So we went ahead and actually modeled this skull as a solid using the BIOS model by studying the porosity and also the permeability of this skull in the actual solid model, and then see what actually happened. So let's look at the same transmission line. You can see here, for the forward propagation, we still get the total transmission through this bilayer. And here I cannot plot the pressure inside the skull because it's a solid model. And in the solid model, for the final element, what retains is just the displacement field and not the pressure field. That's why I cannot plot the pressure field here. Okay. And how about the backward scattering? So let's study that. What happens is you still get some total transmission. But what's funny here is you start to see some interference pattern, not on the incident side, but on the transmission side. So the variance of the amplitude here, we assume our hypothesis is that because of the incidence of the ultrasound onto the solid here, it will result in some mode conversion, especially the shear wave in the skull may take some kind of role that result in the variance of the transmitted sound wave through the skull. But still, you can see the variance of the transmission is still very low. So we hope this is not going to affect much of the B-mode imaging when we are using this non-Hermitian complementary metamaterial on top of the skull. So we went ahead and then do the brain imaging modeling using the BIOS model and then see how it looked like with the solid model of the skull. And you can see we look at the same imaging field and the same imaging line using the ultrasound probe. And then you can see pretty much nothing with this solid model of the skull, which is just the reflection of the skull. Okay. But with the non-Hermitian complementary metamaterial here, what we will see is we still see the shadow, which is scattered by the brain tumor. And that shadow helps us to reconstruct the image in the B mode. Okay. So the question is, how do we realize this non-Hermitian complementary metamaterial, right? This just remains in theory. And to make it to be like a real life application, we really need to actually build this. But the question is, well, since you need to have negative parameters for the metamaterial, which is the direct opposite of the skull, for the real part, people already realized that in the metamaterial community by using the monopolar resonance and dipolar resonance. The question is, how about the imaginary part? The imaginary part in the skull is lost. And if we want to have a direct opposite in the metamaterial, which means that we need to have gain. Okay, so this dates back to the project I work with Mark at Berkeley. We actually use an active metamaterial to actually achieve the acoustic gain. So the story is we can try to use a feedback circuit to connect two pieces of PCT. One is serving as the sensor and the other is the transducer. So once we read the signal from the sensor, we can actually send the signal through the circuit, and then through the feedback, we can adjust the output of the transducer and then trying to adjust the effective medium parameter of this unit cell such that we can achieve an artificial gain for acoustic metamaterial. So the theory here is because the reflection and transmission is actually a combination of the passive reflection and transmission plus the active reflection and transmission controlled by the circuit. And the active reflection and transmission are actually can be controlled by this gain material, not gain material, but like the gain parameter in this feedback loop. So what happens is we can try to design this gain parameter in the feedback loop such that we can modulate the reflection and transmission. And once we modulate the reflection and transmission, we can achieve the effective medium parameters that we want. So, sorry, I'm going in the wrong direction. So this is our design. Inspired by the previous design, we can actually use a 3-layer of the material. So the purple layer is actually the hydrogel. which couples with the water easily because like the hydrogel has mechanical parameters very similar to water. So this will achieve coupling, and we put the air gap in between so that we isolate the sound wave through propagating directly through the unit cell. And instead, for the transmission, it will only be emitted through the circuit, through this feedback circuit. Okay, so we can easily control the transmission because it will only have the active part. We don't need to worry about the passive part. There's no passive transmission because of the isolation of the air gap here in the unit cell. But for the reflection, we need to actually measure what's the passive reflection from the structure, and then we need to add on top of this active part of the reflection. And here is the design of our circuit. So we will have this all-pass filter that gives us the control of the phase, which we can actually adjust the resistance of this R1 and then achieve any kind of phase. And then for the amplitude control, we use the similar all-pass filter, but instead we can actually adjust this R4 to actually achieve an acoustic gain, where the energy is actually supplied by this op amp here. Okay, so this is our design, and the G2 structure is going to be similar, but it's just flipping the direction because it will control the back reflection or backward propagation. Okay. So now, as we mentioned, we need to first measure the passive reflection, and the passive transmission is just 0 because of the isolation of the L gap. So we can know what's the passive reflection, and passive transmission is 0. And to get the total reflection and transmission, we need to actually use the circuit to calculate what's the active reflection and transmission by changing the gain G1 and G2. And by changing the G1 and G2, we can then achieve an arbitrary total transmission and total reflection in our metamaterial. And then by changing the gain in the calculation, we can see that for the density and the bulk modulus, what kappa here is the bulk modulus. So what happens is we normalize all these parameters to the scale parameter. So our goal is to actually achieve the real part of the density, imagined part of density, and real part of the bulk modulus, and imagined part of bulk modulus to be -1. So you can see here, by adjusting the circuit parameter, which is the R1 resistance and R4 resistance here, what we can do is we achieve a -1 value for the real part of density at 1.5 megahertz. Same thing for the bulk modulus at 1.5 megahertz. And same thing for this imagined part. So in this case, we can use the design to go ahead and then make our metamaterial. So this is the sample that we make. So you can see there's a small PCT serving as the sensor and the big PCT back there serving as the transducer to send all the ultrasound. And this is embedded into this hydrogel. And then in between there, there's an air gap, as you can see here. And then on the other side, there's the same structure there. And then we have the circuit connected. So my student is now trying to test the effective medium of this structure by directly measuring the passive reflection and transmission. And later, we also measure the effective median parameters of the skull, which is an ex vivo skull that we have in our lab. This is a human skull, and you can see, as expected, without the skull, when you have an incidence wave, you have a very high transmission. But with the skull, you would expect a very high reflection here, and the transmission is very low. So my student has this result now, and he is trying to retrieve the effective medium theory or effective medium parameters of the human skull. And then once we get the effective medium of the human skull, we can actually adjust the circuit. And then hopefully soon we will put this skull together with the metamaterial to achieve total transcranial ultrasound. And then later we can actually use this metamaterial for the testing of the BMO imaging in our lab. So the other story I want to actually share with you is the therapy. So we just talked about the imaging. How can ultrasound be used for the therapy? So more particularly, I'm going to actually focus on 2 diseases we are currently interested in treating. One is called cerebral venous sinus thrombosis. This may sound a very long name, but I can use one word to talk about it, which is called stroke. Okay, so it's a type of stroke, but what happens is, normally when we talk about stroke, we are talking about blood clot formation in the artery inside the brain. But the difference between the cerebral venous sinus thrombosis and the normal stroke we have in the artery is in this so-called CVST, what happens is we actually have the blood clot formation inside the venous sinus here. So you can see this is the autonomic structure of our brain. And you can see we have this complicated structure of the venous sinus. And then the difference between this venous sinus structure and the artery we have in the brain is, if you look at the diameter of the venous sinus, it's about 1 centimeter in the diameter. But if you talk about the artery diameter, it's about 2 millimeters. So we are talking about 5 times larger vessels here. And you still can result in this kind of blockage from the blood clot. So what happens is, why there's blockage of the blood clot? It's usually because of some stimulation that the platelet was actually activated and then forming this fibrinolysis structure that result in the cluster of the red cells that clot the blood vessel here. So CVST is a real case because we are dealing with the much larger vessels, but with the COVID, now it becomes very common because the COVID virus can actually induce the activation of the platelet inside the sinus and then result in the blockage of the sinus. And once you have the blockage of the sinus, it's very, very dangerous. I am not sure if you heard about there was side effect of the vaccine of the stroke, especially in young women. That's what happened. So they actually have blockage in the venous sinus. And once you have the blockage of the venous sinus, what happens is the blood flow is trying to flow back to the heart. But because of this blockage, what happens is the pressure will build up. And then eventually it will tear apart the blood vessel and then result in hemorrhage that will actually be fatal and then cause death. So the question is, how do we treat this CVST? Particularly because this CVST was real previously before COVID. So there was not much focus on this disease. And there was no specific treatment for this disease because of the large vessel. The treatment that can be used for the artery is focusing on small clot with the diameter to be smaller than 2 millimeters. But now we are talking about clot that has the diameter to be much larger, like 1 centimeter. How can we use those previous methods to actually treat it? The answer is there's no way you can use the previous method to treat it. But instead, what happens is you just put hope that by injecting the drug, which is the so-called TPA, to actually resolve this fibrinolysis structure and then have the clot to be break apart. But that's not efficient. And also in the clinical trial, only 2/3 of those cases, and also those cases are very minor cases, can result in blood flow restoration. For 1/3 of those cases, they turn out to be severe and then end up being dead at the end. Okay, so this is a life-threatening disease, and we don't have any clinical method to treat it. So that's why we focus on this disease. The other disease we are trying to focus on is called the pulmonary embolism, which is also life-threatening. And currently, the treatment of this disease is also real because of the size of the clot you can see here. So what's pulmonary embolism? What happens is you usually will have blood clot formation in those deep veins, especially in the leg. And then those large clots can be dislodged and then accumulate through the infernal vein cover, going through the right ventricle, and then getting into the pulmonary artery. And once it embolized into those pulmonary artery, what happens is it will result in the blockage of the circulation inside the pulmonary circulation, and also it will block the gas exchange. So usually the patient won't be able to breathe in this case. And what's worse, the pressure will build up in the right ventricle, result in the heart failure. So this is actually the third most common cardiovascular disease in the US and also in the world, and resulting in the death of over 200,000 patients in the hospital without any effective treatment. So that's why we are trying to focus on these two diseases. So what's the current treatment? For less severe case, people are trying to use catheters. And this is a 24 French catheter, which was proven to be safe to going into the pulmonary artery. So if you are not familiar with 24 French, what it means is the diameter of the catheter is about 8 millimeters. And then we are dealing with the pulmonary artery, which is about 2 centimeters. So you can see the difference of the catheter diameter and the artery diameter. And what happens is, once you have the catheter gets into the pulmonary artery, the structure of the catheter will deform, and then they try to pull the clot out by lodge onto the clot, and then just pull it back. But do you see any problems with this method? Do you see any problem?
You have long distance to travel.
Long distance to travel, that's one problem. But more severe problem is you have this catheter structure touching the vessel wall. So they are in contact with the vessel wall, and those are sharp structures. It's very easy for you to actually damage the vessel wall and then tear them apart, result in hemorrhage that will cause life. So that's the problem of this current treatment method. And for more severe case, you will need to actually open the chest and then doing the very bloody and very high risk surgery. I actually have a video that I'm not going to show here, which is shared by my collaborator in the Grady Hospital. That's one of the severe cases. He actually opened the chest and then do the surgery for like 4 hours. And that turns out to be very bloody and very high risk. So the question is there a way we can design a better method in treating all this disease? So it turns out that people are trying to study if ultrasound can help, and that leads to something called sonothrombolysis. And the principle of the sonothrombolysis is based on something called acoustic cavitation. So if you are not familiar with acoustic cavitation, it's a principle that's similar to what we usually do by boiling waters. But look at this phase diagram here. When we try to boil water, we usually just like increase the temperature to bring it into the vapor phase, right? But for acoustics, we are not trying to actually change the temperature, but instead, because acoustic wave is a pressure wave, so we can result in oscillation of the pressure. And then once the intensity of the ultrasound is high enough such that the pressure can bring the this phase diagram down into the vapor phase, then we will result in the formation of bubbles. And that's the working principle of the cavitation. And what's interesting is when this gas bubble is formed near some solid, because of the asymmetry of the pressure around the bubble, the higher pressure side away from the solid will just push the bubble and then deform the bubble, resulting in this kind of something called microjetting. And this microjetting will just damage the solid part. So that's the working principle of the acoustic cavitation. And it was actually observed and found first by the Navy. And that's something they were trying to avoid. So what they didn't understand what happens for their propeller when they see this kind of wearing effect after long use. What happens is when you have this propeller, which is like propelling the submarines underwater, what happens is they create a low pressure region outside the propeller. And in this case, what happens is because the pressure is low enough, they form this vapor. And then because it's near the solid space, so the cavitation results in the microjetting and then result in the damage of the propeller. That's what the Navy is trying to avoid. And nowadays, there are some fancy designs, especially for the Virginia class here in the US, for the submarine, that can avoid this cavitation. But as a biomedical engineer, instead of avoiding this, we are trying to use it. So what can we do? Let's try to see when we shine an ultrasound onto this blood vessel, what happens? We can actually use the high intensity ultrasound and then trying to actually bring the pressure to be low enough such that we form the cavitation around the blood clot, and then try to use the cavitation to edge away this blood clot. But previously, people do it non-invasively, and the efficiency was very low. So it was not very effective in treating those two diseases. Instead, nowadays, people will try to put the ultrasound transducer into catheters, and then going through the same vessel, you will directly have the ultrasound inside the vessel, which is called endovascular ultrasound. And then by forming the cavitation near the blood clot, we can try to edge away this blood clot here. But let me give you some statistics. For this endovascular ultrasound, you will need to have 15 hours in order to restore the blood flow inside the vessel. Talking about the traditional TPA drug treatment systematically, what happens is you need about 20 hours. So you basically just improve it by 5 hours of treatment. But we are talking about disease that's life-threatening. The patient is dying on the table. We need some immediate treatment that's immediately effective in order to save life. So this 15-hour effectiveness is not going to be very useful in saving the life of the patient. So what can we do? Let's first talk about what's the problem of this endovascular ultrasound. You can see here, what happens is we just send a plane wave towards the blood clot. So in terms of ultrasound and blood clot interaction, what happens is it usually just results in longitudinal stress onto the blood clot because the ultrasound, plane wave ultrasound is a longitudinal wave. So normally you will just have longitudinal stress inside the blood clot. But remember, those clots are actually formed by the fibrinogen structure. They are usually resistant to the longitudinal stress or the normal stress. But this fibrinogen structure is not resistant to shear stress. So the question is, how do we induce the shear stress inside the endovascular ultrasound? So the answer lies into this so-called Vortex ultrasound, which I studied with Mark back at Berkeley. We try to use this so-called acoustic orbital angular momentum to achieve high-speed communication, and now we try to use this same Vortex ultrasound to treat the disease. So what's this Vortex ultrasound? The Vortex ultrasound actually have this vortex wavefront when propagates. So you can actually take a look at the particle flow or the fluid flow when the vortex ultrasound is propagating inside the fluid. It will result in this shear flow here. Okay, so we did the full wave simulation for the blood clot. You can see that for the traditional non-vortex endovascular ultrasound, it just results in this normal stress, which just push the blood clot back and forth in this direction, in the longitudinal direction. With the vortex ultrasound, it will result in a shear along the azimuthal direction. And this is the shear that we will use to break the fibrinogen structure to break the blood clot faster and more efficiently. So we actually also calculated what's the shear stress along the azimuthal direction, and you can see we actually result in a 4-fold increase of the shear stress inside the blood clot using the vortex ultrasound. Okay. And the question is, how do we actually achieve this vortex ultrasound inside the vessel? So we actually use this catheter, and then we integrate the 4 transducers inside the catheter with a quarter wavelength shift in the neighboring transducer in order to create the mechanical phase delay to create this vortex wavefront of the vortex ultrasound. So this is the sample we make. We make a vortex ultrasound transducer with the mechanical phase delay, and also as a control, we also make this plane wave ultrasound that's the traditional one and can be used to actually compare. Also, there's another lumen in the catheter that we can actually use to deliver drug and also the contrast agent. Here we use the microbubble or nanodroplet as the contrast agent to enhance the lysis of the clot in our treatment. So we went ahead and then test the ultrasound being generated by this transducer. You can see for the Vortex ultrasound, we can actually see this kind of spiral pattern in the face. But for the traditional endovascular ultrasound, we just see this Gaussian wave pattern. Okay. And also we try to actually see if this Vortex ultrasound can induce the shear flow. When the power is off, you just see those like we put the aluminum powder into the water, and then you just see random branding motion for the aluminum powder when the power is off. But when the power is on, you see this shear flow, or indicated by the indicated by this aluminum powder here. So when we went ahead and then test the efficiency of the thrombolysis using the Vortex ultrasound and the non-Vortex ultrasound. And to actually achieve a fair comparison, we put it on a scale such that we can actually use the same push-through force so that these two results are comparable and they are treating the same blood clot. Okay, so you can see within 30 minutes, this Vortex ultrasound actually lyses through the whole blood clot here and then restore the blood flow. But for the non-Vortex ultrasound, is just barely halfway through. So that's what happened for the traditional ultrasound. And also talking about this traditional ultrasound, it's not the one that we use in clinic. This is already the very optimized version, which hasn't been applied in the clinics yet. And talking about the clinics one, it's even much less efficient than this version of the endovascular ultrasound. So we went ahead and then comparing the percent mass reduction and also the clot lysis speed of these two types of ultrasound. And then what happens is we see that the Vortex ultrasound actually enhanced the mass reduction and also the clot lysis speed by near 65%. Okay, comparing with this state-of-the-art endovascular ultrasound that was not even applied in the clinic yet. And we can also further study what happens if we increase the duty cycle of our ultrasound parameter, and it turns out that when you increase the duty cycle, you can expect the mass reduction rate to be increased, which is kind of expected. So remember that for the ultrasound thrombolysis, we have a very large part relying on the cavitation of the ultrasound. So the question is, by using the Vortex ultrasound, will it affect the cavitation of our ultrasound? Will it reduce the cavitation dosage and then like doing it negatively to actually lysis the clot? So we went ahead and then tried to test the cavitation dosage, comparing the Vortex ultrasound and the non-Vortex ultrasound using our hydrophone. And then we test two things. One is the stable cavitation, the other is the inertial cavitation. Stable cavitation is the vaporization that we see before. So it just forms bubbles, and then it will result in the harmonic scattering, which is the nonlinearity of the bubbles. But inner cavitation is a result of the collapse of the bubble, which will result in the broadband emission of the ultrasound, which will raise the noise floor. And this inner cavitation is the major contribution of the cavitation to lysis the blood clot. So we calculate the dosage of the cavitation for Vortex ultrasound and non-Vortex ultrasound. For both the inner cavitation and the stable cavitation, we have a larger dosage comparing with the traditional non-Vortex ultrasound. So this is actually good news for us. We can actually both achieving the shear stress inside the blood clot and also result in a higher cavitation dosage. Okay, and we went ahead to actually try to study the parameters like the input voltage, duty cycle, and also the pulse repetition rate. And we can see that as expected, if we increase the input voltage, duty cycle, or well, we can actually increase the clot lysis speed and also the mass reduction rate. But the thing is, if we increase the input voltage or duty cycle to be too high, there will be some damage to the ultrasound transducer because of the heating. So eventually we choose to actually have the 80 volt as the input voltage, and we choose the 7.5% duty cycle as our duty cycle for the treatment. And in terms of the pulse repetition rate, we can see that it's kind of a random result, but we do see some peaks over here. One is at the 10 Hertz, the other is at 10 kilohertz. But at 10 Hertz, we do see some damage because of the heating of the transducer. So instead, we choose the 10 kilohertz as the pulse repetition rate in the treatment. And in terms of the feeding in speed, what happens is you can see that for high feeding speed, you definitely will expect a much larger lysis speed. But the mass reduction is much lower because since you move faster into the blood clot, the leftover on the side of the blood clot will be more. So what ends up you will actually have a much narrower channel, which is not good for the treatment. So eventually we choose to actually use the 3.3 millimeter per minute for our feeding speed. And you can see that also this will give us a reasonable push through force. Hopefully this doesn't actually damage the vessel wall. To see that, we use the ex vivo bone wide jugular vein and then directly shine it with the vertex and non-vertex ultrasound. And you can see that with this H and E stem of the vessel wall, there's no much difference between the control and the vertex and non-vertex ultrasound, which tell us that there's no damage caused by the ultrasound in this lysis treatment. And also, we went ahead and then test the remains of the blood clot. Remember that this blood clot is large, and when we try to break them, they will form small fragments. The thing is, if the small fragment is too big, they will embolize into the distal arteries. That will result in problem in the distal region. So we need to actually have the remains to be small. So we went ahead and measured the remains, and it turns out that most of the remains are smaller than 100 micron, which is safe for the distal arteries. Okay. And also for this endovascular treatment, the other safety test, which is standard, is to measure the hemoglobin, which is the standard to tell us if the hemolysis happens. And what it means by hemolysis is it means that you are breaking the red cells and then result in the release of the hemoglobin into the plasma. So we test the hemoglobin in the plasma-free solution. What happens is over the 30-minute treatment, the hemoglobin level is less than 20 milligram per DL. And usually the sign of hemolysis happening is when this value is above 40. Comparing with the existing treatment inside the blood vessel, the omni wave is 228. For sure, there's hemolysis. And then histotripsy and angiojet, that's the now the gold standard of the clinics. You can see a lot of hemolysis, which is just killing your red cells. So in terms of safety, our technique is much better. Okay. So we use the ultrasound parameter and then just went ahead and then test it with this 3D phantom model. And we have the blood clot here inside. And then I'm not sure if I can play this video. It's just a video showing that my student actually pushed this catheter into the blood clot and then it lyses the clot through. And I guess I don't have time to actually play this video and it's not working here anyway. But eventually you will see that the blood clot is being lysed through and the blood flow actually restored within 8 minutes. Comparing with current clinical use is 15 hours. So this will be a life-saving tool for this CVST or PE. And in conclusion, I just share with you our research story about the medical application of the acoustic metamaterial and also the Vortex ultrasound. In terms of transcranial ultrasound brain imaging, we can actually design the non-Hermitian complementary metamaterial to match with the acoustic impedance and the skull of the skull, and also trying to counteract with the intrinsic loss due to the skull porosity. And my student is now testing the samples, trying to actually achieve the total transmission through the skull. And then the next step will be trying to actually use that to achieve BMO images through the skull. And for the Vortex ultrasound that we actually developed, we actually show a very efficient lysis of the blood clot, and also it's going to be safe in treating the cerebral venous sinus thrombolysis and also pulmonary embolism. So here I would like to thank my funding agency from NSF and also ONR. Thank you very much, and any questions?
Thank you very much, Chengzhi. That was a lot of information. Good, very nice project.
Thank you.
So, I mean, please, in the audience, if you have any question, feel free to open your mic and speak it.